Welcome back, everyone. It's a pleasure to introduce two speakers in this session in the afternoon. Our first speaker is Jessica Redd from the University of California in Los Angeles, and she will be talking about autonomy in space and other strictly ordered domains. Did everyone get a handout? Yes, okay.
Thank you. Thanks. I'm pleasantly surprised at the extent to which the things that I've been thinking about overlap with the things that a lot of you have been thinking about, which I think is the hallmark of a well-organized conference. So I'm very grateful to be here and to have your feedback on some of the stuff I've been thinking about. I think a good way of thinking of my talk today is as a sort of building on a lot of the things that Peter spoke about earlier. In particular, I'm interested in thinking about the extent to which different entities, types of entities, like degrees, times, and locations in space, what they have in common. And because I'm a linguist, I'm looking at that question from the perspective of natural language. In particular, I'm going to try and argue that there's natural language evidence that the domains of space and time and gradation are sort of fundamentally geometrically or physically, metaphysically similar. Which is to say, I'm going to argue that natural language encodes relations between these things. So relations between two times, relations between two locations, and relations between 2 degrees. And that the encoding of these relations hopefully across languages, behaves in a particular way that reflects a commonality between these things. So I'm going to spend the first sort of 2/3 of the talk giving you some data from English, and so hopefully we'll all be able to sort of access that. The last third of the talk will just be my semantic analysis of these data, and I'll try and stay as informal as possible, but for those of you who are interested in formal semantics, you'll see some lambdas and other sort of calculus there. I'm hoping to make cross-linguistic claims, but the data I discussed today are mostly in English. So one of the things I'm interested in hearing about from you is the extent to which these data are cross-linguistically robust. So at the end, if you have any advice or input on whether or not this works in a language you're fluent in, I'd love to hear it. So, like I said, I'm sort of there's a lot of overlap with a lot of Peter's assumptions. There's a few terms I'm using slightly differently. So the term domain I'm using to refer to types of semantic entities. So usually when we do semantics and predicate logic and things like that, we do it with respect to individuals. So we think of this is an individual, I'm an individual, this podium's an individual. And as we look at other phenomena in natural language, we have to start thinking about other types of things. So degrees, times, and locations, things other than individuals. So that's what I mean by domains. Each of these form their own domain. I am a degree semanticist by training, which means that I spend most of my time thinking about the meaning of adjectives and anything that displays gradation. And that's where this talk begins. There's a puzzle that's been brought up in degree semantics, and in particular with respect to comparatives, like taller, shorter, faster, slower. And in the literature, linguists, in particular natural language semanticists who have noticed this phenomenon, give it a language-specific analysis. They say, there's something about language that explains this asymmetry that we see in comparatives. So I'm going to start by presenting that asymmetry. I'm then going to try and argue that it extends outside of comparatives, in particular to locations in time. And then I'm going to accordingly try and give it a non-linguistic or less linguistic analysis, something that relies on constraints about how we view the world, in particular space, time, and degrees. So here's the original puzzle. I'm looking at the two sentences in one. The first one involves a positive polar comparative, faster, and the second involves a negative polar comparative, slower. So the claim is that 1b, the one involving the negative comparative, has a variation of meaning that the first one lacks. The people who initially observed this difference refer to it as an ambiguity. I'm not going to use that term, and you'll see why. So let's look at the first context at the bottom, the US context. So I'm going to ask you to evaluate these sentences in a context which I've dubbed the US context. And it's one in which the highway has speed laws that impose a maximum, let's say 100 kilometers per hour, and a minimum. So in order to drive legally on the highway, you have to be between 65 and 100 kilometers per hour. In this context, both of these sentences seem to relate Lucinda's driving and Lucinda's speed to the maximum. So 1A, Lucinda is driving faster than is allowed on this highway, seems to be true if she's driving above 100 kilometers per hour. Native English speakers, I've found some speaker variation in terms of these sentences. You might prefer driving faster than she can on this highway. That's fine as well. Any sort of possibility modal will do. And then the negative polar comparative in 1b is also supposed to relate Lucinda to the maximum speed. In particular, 1b in this context is judged true if Lucinda's speed is under 100 kilometers per hour. So as long as she's within the range. So far so good. The difference between the two sentences is supposed to come in when we change the context a little bit. I've called this the Latvian context to try and be relevant. I'm just going off of what Wikipedia told me about speed limits. There's actually a page on Wikipedia about speed limits across the world, so blame Wikipedia if I'm mistaken. But let's just suppose that highways in Latvia differ in that they don't impose minimum. So you can drive on a highway in Latvia as long as you don't exceed 100 kilometers per hour. So this is a slightly different context in that there's no minimum. The judgment is that in this context, the first sentence, 1a, has the same meaning, but the second sentence has a different meaning. So again, the first sentence, 1a, is true whenever Lucinda is driving above the maximum. So let's say if she's driving 120 kilometers per hour, the sentence, Lucinda is driving faster than is allowed on this highway, is intuitively true. But in contrast, whereas in the first context, the negative polar comparative related Lucinda's speed to the maximum, the intuition is that in this context, the negative comparative relates Lucinda's speed to the minimum. So the sentence, Lucinda is driving slower than is allowed on this highway, is true if Lucinda is driving slower than the minimum. So for instance, slower than the maximum. I may have messed this up a little bit. In the first context, the US context, Lucinda is driving slower than is allowed on this highway. It means she's driving under 65 kilometers per hour. And in the second context, it means she's driving below 100 miles per hour. So let me just reiterate. The positive comparatives relate Lucinda's speed to the maximum in each context. But the negative comparative relates Lucinda's speed to the minimum and maximum, respectively. So I've written the semantic generalizations near the bottom of the page. Positive comparatives relate a degree to a maximum, but negative comparatives relate a degree to a minimum or maximum, depending on the context. So this has been referred to as an ambiguity. In particular, the people that I cite here for the data say that the negative polar comparatives are ambiguous, but the positive polar comparatives are unambiguous. I'm not using that term because ambiguity usually means that in a given context it can have one meaning or the other. But as I hope to have shown here, whether you get one meaning, the below the minimum meaning, or the other meaning, the below the maximum meaning, for the negative comparative, has to do with what sort of context you're in. So it's really just an asymmetry. The negative antonym seems to be sensitive to context in a way that the polar antonym isn't. There's another example in 4, if you prefer that example. I should point out, I said I'm only interested in talking about English today, but for some reason, all of the people that have worked on this phenomenon are native German speakers, so I get the impression that the judgment is very robust in German, possibly as well. Let me just briefly say what these people have said about these data. These are all linguists, as I said, and they take these data to represent a linguistic constraint on the difference between, in this case, faster and slower. So they've postulated that the difference here is a difference in semantic complexity of the adjectives. They say the positive adjective just has a relation, it encodes a relation, faster than. But the negative comparative encodes the negation of faster than. So it includes a sort of null not or negation. So it's not just that there's faster and slower. Slower is really not faster, or the opposite of faster. And the semantic account that's provided for these data is that when you've got a slower than comparative, the null negation can take different scope with respect to the modal that you see in the embedded clause, this can or be allowed to. And that's what gives you the ambiguity in their prediction. So the scope is supposed to be the same as something like in a sentence, everyone loves someone. There's there's an ambiguity there. You can say everyone is such that they love someone, or someone is such that everyone loves them. These are intuitively two different meanings. And the way semanticists get the two different meanings is by scoping the two quantifiers with respect to each other in the syntax. That's the same idea here. There's something extra in the negative comparative example that gives us this ambiguity. So just to recap, a comparative I view as a relation between sets of degrees corresponding to the speed and allowances on the speed. This is a fairly standard assumption in degree semantics. And we see an asymmetry between what seems to be a positive relation and a negative relation with respect to which bound of the scale they're relating the first argument to, the maximum or the minimum. The positive one always seems to be relating it to a maximum. The negative one seems to be relating it to either a maximum or a minimum. And the existing accounts of this phenomenon treat it as a linguistic fact. They say there's something about the word slower than that allows for an ambiguity in a way that the word faster than doesn't. So if you turn to the next page, I'm going to try and argue that this is a more general phenomenon. And then I'm going to try and argue that it's best thought of as not a linguistic constraint, but as some other sort of constraint, in particular something to do with the way we view the world. So the sentences in 5 represent my attempt to reproduce this asymmetry for locative prepositions, which I take to be very similar to comparatives, but instead of relating sets of degrees, locative prepositions relate sets of locations or vectors. I've given 2 contexts here, a cold context and a warm context. You'll see that they differ in whether the hut has a floor, essentially, or walls and a floor. So take the first sentence. This is the positive locative preposition. The mouse is above the hut. Intuitively, this sentence is true if the mouse is on or above the roof of the hut. So we get a truth conditions that relates the mouse's location to the upper bound or maximum of the hut. So it's very similar to the comparative in that respect. And in contrast, in the cold context, if you say the mouse is under the hut, you get the impression that the mouse has burrowed under the floor of the house. So that sentence seems to be true whenever the mouse is under the bottom or lower bound of the hut, the minimum. So this is, again, very parallel to the faster than comparative that we saw in the first example. Let's switch to the warm context. We get the same result for the positive above sentence in 5a. If you say the mouse is above the hut and you're looking at a hut that looks like the warm context, you get the impression that the mouse is on or above the roof. So it's above the maximum or upper bound of the hut. But the second sentence has a different interpretation. If you say the mouse is under the hut in this warm context, it's sufficient for the mouse to be below the top of the hut. So this is consistent with the mouse either being in the hut, or if you have a problem with that sort of using the term in, the mouse could be under the eaves of the roof. So not in the hut, but still under the roof. Crucially, the mouse could be above ground in this context, but not in the first context when we use the word under. So in both contexts, the above preposition relates the mouse to the top of the hut, or the maximum of the space. But the negative one, the under, relates the mouse to the top or the bottom of the hut, depending on the context. That's the claim. I'll end up claiming that the important difference between these two contexts has to do with the floor, whether or not the object itself has a salient bottom endpoint. There's another example in 6 that shows the same asymmetry. Notice that I've formed this example from the comparative itself. So I think this really highlights the relationship between the adjectival comparative clauses and the same asymmetry in the locative prepositions. So again, we have a very similar semantic generalization. Positive locatives like above relate an individual to a maximum, whereas negative locatives relate an individual to either a minimum or a maximum, depending on the context. So this seems like a very similar asymmetry. I'll just extend it to times now, but I'm going to be focusing on degrees and locations for the remainder of the talk. But I'll show you that I think we can replicate these data for times. What I'm going to be doing is, instead of giving you 2 contexts, I'm going to be giving you 2 pairs of sentences. And they're going to be taking advantage of a difference between events that we heard about a little bit earlier, in particular the difference between atelic and telic events as captured by Wendler. Effectively, what I have in mind is just the sort of test that Wendler uses for this difference. You know you have an atelic event if you can modify it with a for prepositional phrase, at least in English. So I have an event, Mary was single. You can say for 3 years, but it seems weird to say in 3 years. And that's a good indication that you're dealing with an atelic event. You contrast that with climbed to the top of the mountain. You can say John climbed to the top of the mountain in 2 hours, but it seems weird to say for 2 hours. And so that's a good indicator that you've got a telic event. The difference isn't too important, but that's exactly what I'll be taking advantage of to show you the asymmetry in events. I'm giving you 2 different sorts of events, but what I'm really doing is assuming that we can get at the runtime of an event using a homomorphism. So there's some sort of mechanism that allows us to map an event to the set of times that constitute its runtime. And it's those times that I'm really going to be thinking about. So I'll just show you this asymmetry for before and after, which Peter referred to as temporal prepositions, which I think is a very good way of thinking about them. So like I said, instead of two different contexts, I've got two different pairs of sentences. The first are similar to the cold context or the US context earlier. Mary met John after she was single is intuitively true if she met John after the end of her being single, right? Not after the beginning of her being single, after the end of her being single. In contrast, Mary met John before she was single relates the meeting to the beginning of the period of Mary being single. So just as before, this sort of context illustrated a difference between tendency to relate to the maximum and minimum, we've got a difference between whether the adverb relates the meeting to the end or the beginning. In the second pair of events, of sentences, we've just got a different type of event. And this shows a sort of difference with before, but not with after. So if I say, Mary met John after he climbed to the top of the mountain, again, we're comparing the meeting to the end of the summiting event. All right? So in both cases, after is comparing the meeting to the end of the other event. But in contrast, Mary met John before he climbed to the top of the mountain. Seems to intuitively relate the meeting to the end of the summiting event, not the beginning. So it seems as though 8b is true if Mary met John on his way up the mountain. It doesn't require that Mary have met John before he started climbing the mountain. So again, it seems like we have a very similar semantic generalization, which I've listed after 9 on the handout. After relates a punctual event, the first event in the first clause, to an endpoint or telos of an event. Whereas before relates a punctual event to either an onset or an endpoint, depending on the context or type of event. And I think this is very similar to the pattern that we've seen in the adjective of the comparatives and the locatives. So let me do the interim summary on the bottom of page 2. I'm assuming that these are all relations. What I've done is gone through 3 different sorts of relations. The first relation is a relation between sets of degrees that arise from my use of gradable predicates. The second was a relation between sets of locations, or vectors, if you want to think about them that way. And then the third is a relation between sets of times, or temporal intervals. It seems as though the positive relations have uniformly used maxima as endpoints. So when it's relating A to B, it's relating A to the maximum of B, or the highest point. Whereas the negative relations don't seem to be consistent in this respect. They seem to be relating A to either the minimum or the maximum of B, depending on the context. And again, this has been referred to as an ambiguity of the negative relation in the linguistics literature. But there really does seem to be a difference, a sensitivity to context in one but not the other. I think we've seen a bunch of reasons why it would be a bad idea to extend the very specifically linguistic analysis I mentioned that has been provided for the comparatives to these other examples or to the phenomenon generally. The first reason is that, as I said, the negative sentences don't seem to be ambiguous. We seem to be able to predict quite easily, for a given context, which reading the negative relation sentences will receive, which is not usually a hallmark of ambiguity. And it means that we don't want to posit an analysis which lets us freely have either meaning as a linguistic matter and not as a matter of context. The scoping analysis that I introduced to you earlier relies on the idea that the negation, the null negation encoded in slower, or the negative relation, has something else to scope with. So everyone loves someone is ambiguous from the same perspective because everyone and someone are both quantifiers and they can move around in the logical form with respect to one another. If we want a similar account for the ambiguity of these negative relations, we need to make sure that the negation we're positing for the negative one has something to interact with scopally. And while that was the case for the Lucinda examples in 1, it's just not the case for my other examples. I've avoided quantifiers and modals in all of these other examples. There just don't seem to be any linguistic corollary of the modals in sentence 1 in all of my other examples. So we really just can't extend a scoping analysis to these sentences because there's nothing for the negation to scope with. And so that point is made in, at the top of page 2 as well. Finally, it's not clear to me how to best make this point, but I think it's an important one. It's certainly for my thesis. Also contrary to the scoping analysis, this asymmetry between positive and negative relations doesn't seem to be a property of all sorts of relations. In particular, I think Peter mentioned this, you can have relations between individuals as well, this sort of thing we're used to talking about when we talk about natural language semantics, the podium, me, and this bottle of water. A relationship between individuals is father of or hairdresser of, so forth and so on. So we can try and replicate this asymmetry for individual relations, and I would argue that we just don't have it there. So the sentences in 10 I take to be positive relations between individuals, and the sentences in 11 I take to be negative relations between individuals. I've just negated them. And there doesn't seem to be a difference in how the internal or embedded argument is calculated. So Mary met the guests who could speak Italian. If you think of the guests who could speak Italian as picking out a plurality of individuals, it seems to relate the meeting to all of them, the maximum entity, the maximum individual, the whole group of people who could speak Italian. When you negate this relation in 11b, Mary did not meet the guests who could speak Italian. We're doing the same thing. It's not the case that she met all of the guests, something like that. So I don't think this asymmetry extends to the individual domain, although I have some questions about what has been argued to be an ambiguity of relative clauses that we can talk about at the end if you're interested. So because there's no noticeable, or at least corresponding difference between the way individual relations are interpreted, I'm going to capitalize on that fact and try and explain the asymmetry in terms of a property that I take to be intrinsic to the domains where we do see the asymmetry, in particular the degree, the time, and the location domains. So my analysis starts in section 4 on page 3. This should say economy of bounds. So I'm mainly trying to claim that the asymmetry we see is not the result of a linguistic constraint. It's going to be a combination of what these things mean and how we tend to perceive the world. So I'm first going to introduce the assumption that Peter, I think, has been arguing for as well, that degrees, locations, and time have in common that, at least in a particular context, if you get a set of them together, those things form a strict linear order with respect to each other. And then I'm going to talk about how I think the way we most naturally perceive space and time and so forth affect this. So one important thing is I'm going to sort of change the way we've been thinking about what counts as a maximum and a minimum. I want to argue that that's what counts as a maximum and a minimum isn't an objective fact. It's always relative to the relation we're considering. So the first step in this argument is realizing that the antonyms in all of these relations that I've been discussing are duals. So if it's the case that A is taller than B, then it's the case that B is taller than A, and so forth and so on. What this effectively means is that what counts as really tall is the opposite of what counts as really short. So all of these relations, if you take fixed points in space or fixed degree points, they reverse the ordering of each. Really, that just means that 6 feet as a degree is high on the tall scale relative to 5 feet. But 5 feet as a degree is high on the short scale with respect to 6 feet. All right? That's just a consequence of the entailment pattern you see in 12. So maximally tall is up here, maximally short is down here. So I've been using the terms maxima and minima as just sort of objective truths, but I'm going to switch to talking about them as relative to the scale that we're discussing. And just to make it a little easier, because I've already used the terms maxima and minima, I'm going to talk about lower and upper bounds, upper and lower bounds for each scale. Natural language semantics, at least, if not us as users of language, we're sensitive to these orderings. So if I say John is very tall, what I mean to say is that he's significantly above the tall standard on the tall scale. And if I say John is very short, I mean he's significantly below the short standard on the short scale, or above the short standard on the short scale, which means he's below the standard. So this difference in direction or ordering is something that we attend to, at least as native, linguistic users. I'm going to assume that we've got a maximality operator in our semantics that cares about this sort of thing. I'm not going to go through the details of this too much, but I do want to draw your attention to my at least one aspect of my formalism. I'm using this big X to range over sets of entities, and I'm not specifying what sort of entity I have. So this definition could be talking about degrees or times or locations, but the big X ranges over sets, and the little x ranges over atomic entities, which are members of these sets. X can be a degree, in which case the big X is a degree scale. X can be a location, in which case the big X is a vector, or X can be a time, in which case the big X is a temporal interval. So all I've done in 14 is give you a formal definition of what I've just been saying, namely that to be a maximum degree of tallness is to be up here, and to be a maximum degree of shortness is to be down here. Hopefully that makes sense. A second claim that I'm making is that even though these sorts of individuals aren't intrinsically related to one another in a particular way, they are whenever we talk about particular things using natural language. So for an example, the degree 5 feet isn't intrinsically related in any obvious way to the degree representing 120 kilometers per hour, which is itself not intrinsically related in any obvious way to 20 degrees Celsius. But when we talk about things using natural language, we're narrowing down our contexts in a way that strictly linearly orders these sorts of things. So if I'm using the adjective long, then all of the relevant degrees will be strictly ordered with respect to one another. Namely, any degree will be either taller or either above or below another degree. If I'm talking about the weather, any interesting or relevant degree of hot or coldness will be ordered strictly with respect to one another. So it's not like these domains are intrinsically linearly or strictly ordered, but they are when we use them for the purposes of natural language. I've got some definitions on the top of the right-hand side of page 3 that just illustrates mathematically what I mean by a strict linear ordering, but all you really need to know is that they sort of form a line, and there's never two things that are not strictly ordered with respect to one another. And I'm going to contrast that soon with individuals in the individual domain. What this means for me is that sort of a correlation to this assumption is really what I took to be at least something very similar to Peter's notion of convexity. This means that degree properties encode only monotonic properties. And what I mean by a monotonic is illustrated in 15 for gradable adjectives. If you're not a degree semanticist, which I assume you're not, this might not be terribly easy, but I just want you to sort of think about the sentence, John has 5 kids. So this encodes a dimension of quantity. We know we're talking about quantity of kids as opposed to how pink they are or how tall they are. If it's the case that if it's true that John has 5 kids, then it's also true that John has 4 kids, 3 kids, 2 kids, 1 kid, and so forth. That means quantity, at least as it's encoded in this construction, is downward monotonic. We can infer from one true number reliably to a number below it, but not vice versa. We can't infer from the truth of the fact that he has 5 kids to the fact that he has 6 kids. Many properties in natural language are downward monotonic, but not all of them, as you'll see shortly. Some of them are upward monotonic. But they're all monotonic is the assumption I'm making, which really contributes to the idea that times, locations, and degrees have in common this strict ordering. I'm also going to use the math in 16 to illustrate groups of these things for the purposes of my analysis. So if we have a plurality of individuals, we don't necessarily have an interval. If you are a fan of Link's work, then you think that a plural of individuals is organized into a joined semi-lattice, which basically means that you've got John, Mary, and Bill here, and then you've got a plurality that's John and Mary, a plurality that's Mary and Bill, and some of them, they're not strictly linearly ordered with respect to one another. But all of these things, by virtue of the assumptions I've just argued for, pluralities of degrees, pluralities of times, and pluralities of locations, i.e. vectors, they do form these intervals, and I'm going to represent them accordingly. We can have an open interval, as you see in 16a, with these curved parentheses. What that means is neither A nor B are part of the interval, but they demarcate the end of that interval or the beginning of that interval. Some of you will find this familiar from math class. And in contrast, you've got a partially closed interval illustrated in 16b, where only one of the endpoints is a member of the set. The other one, again, just sort of marks the end of the set. And so it's the difference between really 16b and 16c that I'll be relying on to explain the difference between the two contexts and the two sorts of contexts that we saw earlier. So my proposal is formally represented in 17 and informally shown in right above 17. So for any relation R across domains, I'm going to talk about a relation between A and B. And A is going to be effectively my figure, B my ground. A just corresponds to the external or matrix argument. B corresponds to the internal or embedded argument. So for some relation R, A, R, B, A relates to B, is true if and only if some member of the A scale exceeds, and I've put an asterisk next to that, and I'll explain that in a second, exceeds the greatest closed bound of the B scale. The asterisk under exceeds means that I want exceeds to be order relative, just like my maximality operator earlier. So I want to say exceeds on the relevant scale. So if we're talking about above, I want it to exceed on the above scale. If we're talking about slower than, I want it to exceed on the slower scale. And as I tried to explain, this means that we're going to go in different directions depending on the scale. So it's effectively what I'm saying is whenever you relate A to B, the relation is always going to choose the most informative endpoint possible. And that's always going to be the highest one on the relative scale, the relevant scale. In the case of tall, it's always going to be the highest one up here. In the case of short, it's always going to be the lowest one, which is the highest on the short scale. And I think as long as we assume an important difference between open and closed bounds, I think this can explain the asymmetry that we saw across these domains. So let me illustrate this quickly. The illustration starts in 18 at the bottom of page 3. Lucinda is driving faster than is allowed on this highway. What I've done for the US context is I've taken Lucinda to represent Lucinda's speed. And I'm using the greater than with a plus underneath it relation to correspond to the faster than relation. And I've taken the final thing, an interval, I'm using that to represent what's allowed in this context. Remember that the US context gave us a lower bound of 65 kilometers per hour and an upper bound of 100. The underlining in 18a represents what my theory predicts will be the endpoint that's used in this relation. And in both cases, it's going to be the highest endpoint on the faster scale. So 100 kilometers per hour in both cases, which is in fact the intuition that we set out to account for. If you flip the page to 19, Lucinda is driving slower than is allowed on the highway. Again, I'm relating Lucinda's speed, but I'm doing it with a greater than in the slower sense. So this relation greater than with a subscript minus. And when we think about the slower scale, recall that 100 kilometers per hour is higher on the lower on the slower scale than 65 kilometers per hour. So now 100 kilometers per hour is a minimum on a slow scale, and 65 is a maximum on the slow scale. So 65, when you're coming at it from a slow perspective, is actually the most informative or greatest bound. And in the US context, that's what the semantics uses as an endpoint in the relation. So again, the underline represents what the theory predicts will be the endpoint that the relation relies on. But in the Latvia context, there really is no lower bound or higher bound on the slow scale. There's only one thing: you can't drive above 100 kilometers per hour, and nothing was said about the lower bound. So we assume it's bound by 0 at the bottom, but 0 is not a speed, so this is an open bound on the interval. In this context, 100 kilometers is the highest bound included in the interval by virtue of the fact that it's the only bound encoded in the interval. So in this context, my theory predicts that it's 100 degrees that the relation will use as a point of comparison. I'll just do the hut cases from 5, and I'll skip over the event ones for now. I switched centimeters and meters here. I don't know why. They should all be meters. Let's assume that, oh no, sorry. No, I did this right. In the cold context, I'm assuming that the floor of the house basically represents a lower bound at 1 centimeter. So it's just off the floor. It's an arbitrary point. And then the top of the house is 5 meters. So again, we've got a closed scale, and the highest point on the above scale is 5 meters, and this is what the relation chooses as a point of reference. In the warm context, there is no floor, so there is no sort of end to the house. It just stops at the ground, and so we've got a lower bound of 0 that counts as an open bound on the interval. But again, 5 meters is going to be the maximum in both cases, so this is used as the endpoint for the purpose of the relation. In the sentence in 21, the mouse is under the hut, we've got the reverse situation. And now we've got one of the sentences, one of the contexts, the cold context, has an upper bound that's a member of the set, in particular 1 centimeter, corresponding to the bottom of the house. So this is what's used by the relation as a point of reference for the comparison. But in the warm context, there's only one bound included in what counts as the house, and in this case it's 5 meters. So we have to go with effectively a minimum on the warm scale, or on the under scale, to make this comparison. So there's a lot of complicated math and switching of perspectives here, so let me just try and summarize what I'm saying. What was called an ambiguity when linguists were just looking at these comparatives isn't really an ambiguity. It's not something linguistic. It's just got something to do with the fact that when we talk about speed, we're always lower bounding at 0, and 0 isn't really part of the interval that we're discussing, in contrast with a context in which we have an artificial minimum bound that does seem to be included in the interval. And it's the same when we're looking at gravity and the position of a house. If the house has a floor, we think of that as the bottom of the house. And it's part of the house, and it's part of the interval or vector that's corresponding to the location of the house. If it doesn't have a floor, then the house just sort of artificially stops when we hit the ground. And this is a stopping point or an end point for the house, or at least the vector corresponding to the house, but it's not part of the house, so it's not included in the extension or the vector of the house in the same way. And my claim is that this is what natural language relations attend to. They say, give me something that represents the interval you're talking about. I'm going to take the most informative endpoint that belongs to that interval. And in most cases that we've seen, that's going to be the highest or maximum endpoint. But not in every case. Sometimes when we've got something like an artificial or a 0 bound, we're going to go with a less informative bound. And I think that's what we see when we see this asymmetry. One way of testing this hypothesis is to try and find a context where our perspective on the world is different than these downward monotonic properties. Really what I've been doing is looking at downward monotonic properties. In a way that's consistent with some experiments that have been done on the comparative or Lucinda driving cases. We see that when we switch our perspective, it's actually the positive relation that seems ambiguous and not the negative one. So I think it's easiest to illustrate in the degree case, but I also have a location case in case I have time. So it's the Autobahn context in 25. So imagine the Autobahn is sort of the opposite from the Latvian case. Instead of imposing maximum on the speed on the highway, it imposes a minimum, and only a minimum. There's no maximum. The reported intuition here is that a sentence like 1a, Lucinda is driving faster than is allowed on this highway, really means above the minimum here, so above 70K. And that's different than all of the other positive relations we've seen, which always mean greater than the maximum. So in this case, it's using the minimum as a reference point. But it's still a positive relation. And in contrast, 1b means below the minimum or the closed upper bound. So if you say that, take the sentence, Lucinda is driving slower than is allowed on the highway, it means she's driving slower than 70 Ks, which is, again, the maximum on the slower than scale. So the claim is that when the linguists were looking at these data, at least originally, they said there's something ambiguous about the negative ones. The positive ones are unambiguous. But I've argued, or at least tried to argue, that the ambiguity isn't something linguistic, it's just a combination of what these relations are doing, what they're encoding, and the way we most naturally look at the world. And if we switch the context accordingly, we get a difference between the positive and negative ones. Namely, it's the positive ones that are behaving bizarrely and not the negative ones. And again, I think this all has to do with the fact that degrees, locations, times, all of these things, they have in common this strict linear ordering. And it's something that we pay attention to as speakers of natural language, and it also seems to be something that our relations encoded in natural language pay attention to. Thanks.
Thank you very much. We have time for questions.
Jessica, it's so far outside what I do that I hesitate to even ask, but as you were talking, I found myself wondering about ordered domains in which there's banding. So you consider how wrestlers have banded weights, so there's successive minima, maxima, maxima is the minima for the next one, et cetera, or like layers of the atmosphere, you know, I forget what they are, lithosphere, troposphere, or whatever. So wouldn't that pose a different and interesting case if you have banding? Because you then don't have the default minimum as being 0.
Sure. So it would be more like the U.S. context where there's an imposed minimum, right?
Well, but it would be even like more contingent because there's only one allowable band in the U.S. context. Whereas if there's multiple bands,
I see.
you can be in the right weight class for the, and there's also, wrestling is actually an interesting instance because there's bands, but you can wrestle way below, like the weight, you can wrestle up is what they call.
Yeah.
But you're not well advised to wrestle up because you'll lose. I don't know, I just sort of think you should expand the analysis a little bit, and it might be a challenge.
So if I'm not mistaken, you've picked up on what has been referred to as non-monotonic properties by Beck and Ruhlmann, who have thought about this a lot. So I said a downward monotonic property is one from which you can infer from n to n minus 1. So John has 5 kids, that means he must have 4 kids, 3 kids, and so forth. There's upward monotonic ones, like how much money can a graduate student live on? If a graduate student can live on 5,000 euro, he can live on 6,000 euro, and so forth and so on. But if I'm not mistaken, you've picked up on a non-monotonic.
I guess I don't understand how you're using non-monotonic. To my mind, it's monotonic if it is along a continuum, a single continuum. No? What do you mean by monotonic then?
I have the definition here. The people use different terms to talk about this property. Cumulativity is used in linguistics. It's not clear to me what the relationship to convexity is. That convexity might be more of a three-dimensional version
I'll
of.
check up on it. Like I say, I don't do this.
Well, just in case I can help. There seem to be non-monotonic properties that are at least discussed in natural language. So, if you imagine a context in which, I don't know much about soccer, but let's say the rules of soccer are such that you can have either anywhere from 5 to 8 players on the team. I'm an American, so you'll have to, if that's wildly wrong, you'll have to forgive me. That's a non-monotonic, at least context. So if I can't infer from n to n minus 1 or n plus 1, I can only sort of infer within this range. Those are certainly possible, but you really need to set up a context in order for that to be true. I've claimed here that natural language doesn't encode non-monotonic properties. And it's true, and I think this is similar to a point that Peter made. There's no one predicate that corresponds to something like this. You have to sort of give it a rich context in order to explain it. So I don't know if that helps.
Okay. First, a small side remark. Convexity applies to spaces of any dimensionality, one-dimensional and so on. And I think that monotonicity can be translated into convexity, but let's talk about that later. My comment concerns your analysis of these, what you call ambiguous meanings. And I totally agree with you. This is not semantic ambiguity, it's pragmatic ambiguity. Depending on what the rules are, you get different meanings. That's, I think, the correct analysis. I was reminded of another domain where you may apply similar reasoning, and this is based on work by Stephanie Salt in Berlin, who studied uses of the word most. So if you say most people in the room are rich, the official definition for most would be more than 50%. But pragmatically, you only say most people in the room are rich if there are about 2/3 of the people. she studied how people use these words and so on. So basically it means if you say most people are rich, you mean roughly at least 2/3 are rich. But that means that when you start looking for negations, you say well, most people are poor in the room, they would be more than 2/3 are poor, and so on. And if you then start looking at negations, it turns out to be funny, because if you say it's not the case that most people are poor, then it would be enough that less than 50% are poor, and similarly for most. So the negation will behave differently than the positive case here because of pragmatic reasons. And the pragmatic reason is that there is no point, this is the Gricean point, that you wouldn't say that if there is 51% rich people in the room, you would normally don't say that most people is, because it's not very much of a point of saying it. The Gricean, you want to be informative. And you're only informative if it's about 2/3 that are rich. So I mean, have a look at most and see if you can fit that into your
I have looked.
scale.
I have looked at most. There's a lot of really interesting experiments that show just exactly what you said. That contrary to what you might think, it doesn't mean more than 50%. It's actually quite context sensitive. I've got a lot of work, in fact, a book coming out arguing that a lot of the meaning involved in things like this have to do with your choice of antonym, whether you choose the positive one or fewest. And I have a Gricean sort of manner implicature approach to these data. But the data you gave actually reminds me of something in the individual domain. I don't think anyone's got a good analysis of asymmetry with positive and negative predicates in donkey sentences. So if you say, every man who owns a donkey beats it, he has to sort of be beating, if he has more than one donkey, a lot of them or all of them. So it's a universal interpretation. Just one of them is sufficient, I think, with this case. But the claim is that if you switch the sentence to every farmer who owns a donkey hugs it or vaccinates it, he has to be vaccinating all of them or hugging all of them. So it seems like you've got a difference in interpretation between universal and existential there for the predicates. So there's so much going on with these antonyms, and it's not just these relations. Yeah, great.
Thank you for a very interesting presentation, and just a brief remark about telic events. And it seems that they fit your analysis prettily too, because there is another type of events which can have a teleconstrual too, and in fact they are left bounded. For example, run, you can say, John suddenly ran, started to run, and John ran for a couple of minutes. And we can say Mary saw John before he ran, and Mary saw John before he ran for a couple of minutes. And you have the same ambiguity with before.
So I really like that as a suggestion. So just to explain in case anyone missed it, so in order to test my hypothesis for the degree sentences, I switched to this Autobahn context, where there's a minimum instead of a maximum. And I didn't go through it, but for the locations or the prepositions, I switched to what I call at the top of page 4 an anti-gravitational example, one where there's a bush growing from the top of a cave. So we've sort of reversed it. And I think I make the right predictions for the prepositions in that context. But I hadn't yet come up with a way to test my hypothesis for before and after, because I had been brainwashed as an event semanticist to think of events as only coming in two flavors, telic, i.e. having an endpoint, or atelic, not having an endpoint. And no one ever talks about events having beginning points. But yeah, I think you've given me a great thing to think about. Starting to run is an event that seems to have at least more focus on the beginning or onset than it does on the endpoint. So I'll definitely have to think about that. I'm curious to see whether it works out. Thank you. If there's still time, I might... No.
Yeah, but 2 minutes.
2 minutes. I wanted to point out something that came up in Peter's talk. He gave the contrast between under the shower, I'm standing under the shower, and below the shower, which sounds really bizarre. And under the shower works just like my warm context case. You know, I'm interested in the top of the hut or the top of the shower as an endpoint. But the fact that below doesn't work well for this context, the shower context, really underscores something else that I've noticed, which is to say that below doesn't seem to work like under. Whenever I use a below sentence, I really am always using the bottom, like the floor, as an endpoint. It doesn't seem to alternate in the way that under does. So there's a sense in which I've cherry-picked this data and maybe made it seem more parallel to the other domains. If anyone has any ideas on that, or if anyone has a language that has only one sort or the other, I'd really love to hear about it. Yeah. I see. I see. That makes sense. I'll think about it. Thank you.
Great, let's thank our speaker again. The second speaker in this afternoon session is Karel Ježek. He has a double appointment at the Charles University in the Czech Republic and Norwegian University of Science and Technology in Trondheim, Norway. And he will be talking about neural representation of space, hippocampal memory states and their fine kinetics.
Thank you very much, Alex, for introducing me, and thank you very much for inviting me for this conference. It's a big pleasure to stay here and being able to present my work and work of my colleagues in front of you. So I'll be mostly speaking about memory, about the spatial memory, and about how the brain encodes the space. So we consider the memory as a kind of icon of stability, of something that's formed at one moment and that should last then ideally forever until the death. But in fact, if we consider not only duration of being able to recollect something, but mainly the process of recollection, of memory retrieval, then we end up with an extremely dynamic process that if everything works fine in the brain, that lasts a fraction of a second. And after I introduce how the brain codes the space, at least what we know about that, then I'll jump to a bit of theory about states of activity in the brain and their formal description as attractor states. Then I will finally come to these fine kinetics of memory processing, referred especially to memory retrieval. So, brain is the stimulus processing machine. And if it deals with a space, it deals with a highly complex dimension. So first it has to basically decompose it to its elements and then start to combine those together and at the end to interpret those different informations into some meaningful sense. So this is performed across many, or at least a large number of interconnected neural networks. Those networks can have different architecture, and the type of the architecture, of course, forms their functions. There are two basic types of architecture within the brain neural networks. One is kind of feed-forward, when the elements of a given network don't communicate with each other, so they simply are out as workers in a big factory, getting the information, assembling it together, and send it somewhere else. In the other type of neural networks, we call them auto-associative, or networks which have a lot of collateral networks, or attractor networks. These elements, the neurons in these networks communicate intensively with each other. And these networks have very special properties, can form different patterns of activity, and they are supposed to be kind of a basis for the storage of memories in the brain. So let's jump directly to the hippocampus. Hippocampus is part of the cortex, part of the very old cortex. We call it also archicortex. It doesn't have so many layers as the neocortex. It has only 3 layers. But it's a structure that is complex itself. It's composed out of at least 3 different networks. But, and I will mainly concentrate on the networks of CA3, which is this typical auto-associative network that has a lot of communications between its neurons. And then we have CA1, which is the prototype of the feed-forward network where the neurons don't communicate between each other and they just process the information that comes there from CA3. Very importantly, hippocampus has, of course, many inputs. The main cortical input, and I will mention it thoroughly afterwards, is from the entorhinal cortex. This is the main place where the hippocampus gets its information about space. So in the late 60s and being published in the beginning of 70s, kind of fantastic phenomena which at the beginning no one really believed has been found by John O'Keefe, being able to record cells from hippocampus that specifically respond to the location of the animal. I need to rearrange the mic here. So here you can see my colleague Laura Colkin, who is recording from rat. Oh, excuse me. I need to switch on the sound in my computer. Good. So in this video, you can see the rat that has implanted electrodes into hippocampus. This is the place. The electrode is super tiny, so it really registers the activity of a single neurons and doesn't kill it. So you can really see how the neurons respond to the given location of the animal. So I hope. And this is one neuron tuned in the hippocampus. There are millions of these neurons there. They are called place cells, and they are called in this way because they specifically respond to the position where the animal actually is. So this cell, this place neuron, specifically responds to this area of the known environment, and the activity of its neighbors in the network are, of course, totally different. So you can, this is kind of, this is summarized activity of this neuron. What you can see in the gray, that's the path of the animal within 10 minutes of the experiment, and the red dots are the actual action potentials the given cell was emitting. So across many cells, you can see that those neurons are really specific to the given spatial location the animal is actually in, and their activity within the network covers all possible places in the environment. So these neurons create kind of a spatial map of this environment or spatial representation of the environment. This spatial representation is environment specific. This means that in a different room, and I'll show it later, these neurons would have different activity, and most of these neurons actually wouldn't fire at all. That's the rule, that in the given network, most of the cells is silent and only a subset of cells is coding for something. So, and for the purpose of description, I will basically show those activities of the cells in the form of these rate maps, where the color or the temperature of the color codes for the rate of the given cell. So the higher rate of firing, the warmer color you will see. So this hippocampal representation of space is composed of a group or subset of neurons, hippocampus. That's really reflecting the fact that majority of the cells is silent in a given environment, and in another environment, a subset of those previously silent cells become active, and so on. These cells active in a given environment have different fields, different places to respond. Therefore, we call those fields as firing fields or place fields, and they cover the whole environment. It's not hardwired. These cells need, or this kind of representation needs some minutes to form. So there is some learning occurring, which is dependent on NMDA receptors. They are stable in time, and let's make it a model for kind of as a substrate of spatial memory. If you expose the animal into the given environment one day, second day, third day, you will see still the same representation. And importantly, there are some cells that fire, if you present the animal across 2 rooms, there are some cells that don't fire in one room and fire in the second room and vice versa, and some cells that by coincidence fire in both rooms, but importantly, they have different firing fields. So each room is really encoded specifically, and therefore we believe this is really physiological substrate of spatial memory, because you can see all these features. Another feature that makes us believing this is the kind of tolerance towards changes. If you train the animal in a square environment, as this one, and then actually experimentally in the experiment stretch the environment into this horizontal dimension or vertical dimension, or you simply increase it, the representation adjusts until you do change that makes the environment looking totally different, and then hippocampus simply creates different representation, forms different memory. Importantly, what makes hippocampus does this representation? What kind of stimuli are coming to form it? I mentioned medial entorhinal cortex, entorhinal cortex, and its medial part really brought to the hippocampus spatial information in various forms. This, especially for Peter, is the head direction cell that fires everywhere, but only when the rat heads certain direction. Yeah, it doesn't matter where the animal is, but it needs to look at certain direction. So in this corner, you have then a polar projection of the activity of the cell. And they can be extremely direction specific. The angular responsive tuning curve can be very, very narrow, as actually you can see in this case. Then you have, so that was the information about the angle of moving or angle of heading. And this is example of cell that we believe makes the metric input to the hippocampus. So no sound now, because that would be confusing. You can see the action potentials as a dots on the video, and the video fastens, so we get the pattern in a couple of seconds. So this was something which was, at least at the beginning, hard to believe. But the cells in medial entorhinal cortex, we call them grid cells, form firing fields in a very regular pattern in this kind of triangular or hexagonal way that covers the entire surface of the environment the animal explores. So whereas the first type of cell goes for angles, these cells code the metrics, the dimensions. So these are the rate maps, these are the real spikes, firing rate map, and this is the autocorrelation that nicely reveals the regular pattern of the activity. And importantly, opposite to the hippocampal representation, if you shrink the environment down or up, these cells don't adjust. Yeah? You can see here the 2 meters wide environment shrink to 1 meter, and you can see still the same metrics. So this makes to believe us that this is a really metric system, similar to the system we use for the cartographic uses. Importantly also, this system is very much dependent on the self-motion cues. So in this environment, the animal was presented in light, then in this environment in darkness, total darkness, and this for the control, again, in the light conditions. And you can see that nothing has changed. So the animal didn't see anything here. It could, of course, smell, it could count its steps and angles, but it nicely demonstrates that this metric system, and the same would be for the head direction cells actually, is not dependent on the vision, but it can use it. So for the short summary, for the medial entorhinal cortex, we have these grid cells coding for metrics, and it doesn't matter, they are not responsive towards the angle of movement. Then we have the pure head direction cells that basically fire everywhere whenever the rat heads in a certain direction. And then we have also some called conjunctive cells that are firing across this regular pattern we observe in the grid cells, but only when the animal heads a certain direction. So this is kind of combination of two domains. More recently, in the same place in the brain, medial entorhinal cortex, the border cell system has been found. So this is something more abstract than just space defined by angles and metrics. This really responds to physical borders of the environment, and to be sure that it's not just a firing field, which is very elongated. If you insert a kind of border in the center of the environment, the cell will respond to it because this cell is tuned to borders to the left from our view. And it also doesn't matter whether the environment is squarish or circular. So all these inputs, and I have to say many more, because the number of cells that are coding for these properties in the medial entorhinal cortex is not all the cells we can record. There is still majority of cells that do something, but we don't know what, because we were not able to decode their activity. But definitely at least these three types of cells end up in the hippocampus and form its representation that is then environment specific. So you can see very important transition between qualities that are environment non-specific, because these cells would show you the same image in whatever environment, to pattern of activity that is specific for each room, and that we believe makes the basis for the memory for spaces. So as a concept for memory storage in the brain or memory processing in the brain, Donald Hebb, about 70 years ago, brought the hypothesis that the memory is stored as a pattern of activity of individual cells within the network. And it's not only one cell, as the model of the Christmas dinner cell, meaning that each event of our life would be coded by one cell, or it's not totally distributed across all the cells. It's always subset of cells within given network that participate in coding one category, one memory, one event. In this case, it can be thinking of a cat and thinking of a dog. And there is always an overlap, so you can see that some neurons are active in both these ensembles, both these traces or states of activity, and the rest can be different. So in this way, the network is able to store many, many representations, many different patterns, because the elements can repeat, and there is a lot of combinations the network can use. It's been found, and actually initially proposed by work of David Marr, that these states of activity behave in an exclusive way, in a kind of discrete pattern, meaning that either there is one active at the moment or the other is active, not both together normally. So you might know it from, or we might illustrate it on the flipping pictures, right? Because this is the ambiguous picture that can be interpreted as a faces or as a jar. All you know it. And within the kind of attractor theory, or within this way of thinking, then we think that there are basically two states of activity, one interpreting this ambiguous picture as a faces, second as a jar, but never these two states of activity, these two interpretations can be active together in the moment. They simply flip back and forth. So this is called attractor behavior, meaning that given state of activity, in this case ambiguous one, is attracted towards interpretation of one interpretation or to the other one. For illustration, we depict this situation on such a called energy landscape. So energy landscape means kind of in an abstract way shows how the network spends the energy when coding for the given stimulus. And those ambiguous stimuli or stimuli that are not in total agreement with what's stored are put on the higher energy point, and therefore they are attracted towards the lower energy states. So in this case, basically total agreement between the stimulus and its what's remembered about it would be about this position. But if the stimulus is far from what's remembered, like we have many different types of dogs. The attractor, the basin of attraction of a dogness is extremely wide. So some dogs don't even look like dogs, but they would be very far from the center of the attractor, and they would, because they are still kind of considered as dogs, they would fall into the same attractor. So another example of attractor kind of behavior or perception is this type of flipping cube, which can be interpreted in two ways. And if you insert kind of element that makes it meaningless for both attractor states, you can basically feel the power of the attractor in your brain simply to neglect this distracting element and sticking with one or the second interpretation. This is another example of attractor, which shows that the landscape, the energy landscape, is not fixed representation. It's actually plastic. If you see given stimulus as this letter, which can be considered as a H or A, depending on the context, in this case direction of reading, basically the border, the saddle between those two attractor states moves, so the stimulus falls into the proper state, A or H. The kinetics or relation between attractors is nicely studied by morphing. So far I spoke about basically two states and two kinds of stimuli, but which in this case is a familiar faces, Marilyn Monroe as a one attractor state, Margaret Thatcher as a second attractor state. But you can create actually computer morphed sequence of those faces with different proportion of each state in it, and present these pictures to the probants and ask whether they would consider this face as a Marilyn or as a Maggie. And what you find is a profile where initially about three first stimuli fall into the attractor of Margaret Thatcher, and the last 5 into Marilyn, and the rest is kind of not that categorical across all the individuals. But here, importantly, we call it pattern completing, that within the range of the first or last stimuli, the network pattern completes, meaning the given stimulus is falling into the attractor of either kind. And this basically is what we believe is happening in the neural networks when they code memory, and especially when they recollect this memory. At the beginning, in such a auto-associative, highly interconnected network, some stimulus is presented and subset of neurons becomes active. Because of the long-term potentiation, their connections become more efficient, and these potentiated connections are, of course, stay even after the stimulus is not present, and they form the basis for this ensemble that codes the initial pattern, initial stimulus. After, or when another stimulus, which is very close, very similar, or just a proportion of the original stimulus is presented, because it's not exactly the same stimulus, not exactly the same group of neurons becomes active. But because of those enhanced connections, the original pattern gets completed. And therefore, we call this process as a pattern completion. And we believe that this is the basis of memory recollection. Because whenever you see something you remember, you never see it exactly the same as you saw it for the first time. The world is changing, right? But this is the way how the brain can decode the similarity or how the brain can actually categorize things which it remembers already. This is exactly similar or depicted in these other experiments with morphing, when in these portions of the stimulus morphing you can see the pattern completion, and the opposite process is pattern separation, which happens between those two. Very interestingly, or not that interestingly, but importantly, the same thing was reported on the way or on the level of neural networks. So you can see here two representations. This is always one cell, second cell, third cell, and so on. And you can see that the animal was run in a square environment and then in the circular environment. And those cells, or the network, created two different representations. Yeah, they are really different. Either the cell is not firing and fires here, vice versa, or the cell can have two different firing fields across both environments. Under these conditions, you can actually do the morphing as well. That's what John O'Keefe did in his lab, creating kind of a range of partially or morphed stimuli, morphed environments, and when the rat went through them, they really found pattern completion to some degree when the given environment was no longer resembling the square and became more circular. Then the network switched to the representation of the circular environment. So you can see basically identical picture here, which shows the correlation of the given session with the extremes, with the stored representations. So my main focus is on those really processes that are connected with memory recollection. That has been not studied so far on the level of neural networks. And the main question is how the transition between two representations looks like. Meaning, if you are in a certain state, you are remembering something, or you are in a certain state of certain memory state, then you hear a question, you need to recollect. You need to jump into another memory state. That's the issue. So in this way, hippocampal spatial representations give us fantastic opportunity to study memory processing in general in the brain. And if we are able to induce change across these two representations, for instance, while we are recording the activity in the brain, we would be able to see the dynamics of memory recollection from inside of the brain. So we are not dependent on what the animal or human responds. We just take the information directly from the brain with fantastic, with a great temporal, high temporal density. So, but how to induce it experimentally? Basically, what we had to do is to create a situation which would resemble the teleportation across two different places. Because if the animal is in one environment, it gets all the visual and self-motion cues from it. And if we want the hippocampus activates different state, different representation, different memory, we need to change the spatial stimuli in a step-like way to actually force the hippocampus to change the state. So we trained the animal in two different environments of the same shape in darkness that were connected with a small alley, and they differed basically only by their inner lighting. So in one environment, the light cues were actually located under the floor. In the other environment, to look totally differently, the light cues were on the upper edge of the environment. And initially, the animal was trained to explore this area, so it really understands those two rooms are at two different locations and form two different representations. Then in the next stage, we simply close the connecting wally or alley and presented the animal with those two rooms in a sequence for a couple of days. And in the final stage, we used only one box, one environment that was equipped with both sets of lights. With switching the lights in one way, we could make it as a room A with the lights under the floor, and switching the environment to the second position, the lights to the second position, we could make it as a room B. And in this case, in this stage of pre-training, the situations basically had the common environment, the common location in the room, also the common materials, and the only difference between those two rooms was the light, which you could very easily switch just by the manual switch, while the animal was in. So we were recorded when the animal was freely exploring and switched back and forth every minute for about 10 minutes session, the identity of the environment. And in this way, with switching the lights, we switched the visual inputs to the network. So it needed to somehow digest it. Actually, initially I didn't expect it would have a strong effect. I thought if it works only once until the rat finds out the fooling, right? But I was very much surprised that you can repeat the teleportation 50 times. And there are still two attractor states, and the brain would work with both of them and switch very rapidly. So before I show you the results, just a couple of technical necessities. So this is the ensemble of cells we were recording through those two rooms. You can see that majority of the cells, I'll run it once again, majority of the cells was firing only in one of them and silent in the other one, and vice versa. And very few cells were active in both of these rooms, which gave us great resolution. I mean, we were able to tell with really high certainty which room the animal is in without seeing it, just by reading the actual firing. So these are all the maps we recorded on top of each other, always one cell, second cell, third cell, and so on. And this is example of 1 second of recording in one of the rooms, and basically comparing it, I'll describe this later, comparing it with expected firing, which you can see here, you can just, based on the raw data, tell which room the rat was actually running in, right? Because here you can see that the cell number 8, 9, and 15 is active, which is the cell that was, which are the cells that were active only in the room number 1 or A. So therefore, this sequence of activity was taken from room A. It's really a very transparent way of coding in the brain, in hippocampus. In order to achieve high temporal resolution of the data, because that's what the single cell recording brings you, we use the local field oscillation, local EEG, which is about 9 Hertz oscillation, very dominant in the hippocampus while the rat is running, and cuts the data into temporal bins, reflecting this natural oscillation, which gave us about temporal resolution about 9 Hertz. So 9 times in a second, we could say which room the rat was thinking it is in. And we simply correlated the given activity with both expected representations, and always got one correlation coefficient high. In this case, that was the correlation coefficient with the room A, and second was typically low. So for the teleportation session, you can see here the one sample. The animal was running in a first room A, let's say, coded by red. Then in the time 0, marked with the green line, it was teleported into room B and stayed there for the next seconds. So what you can see here is very fast transition between both states. So the given activity suddenly stopped correlating with what was expected as a room A representation and started to be in agreement with how the network coded room B. And this happened within the first couple of hundred milliseconds. Very interestingly, without doing anything in the outside world, we saw that the network jumped occasionally back to the previous representation. As the rat was thinking, I was in A, now suddenly I'm in B, but I didn't cross to B, so what's happening? And this could come back and forth for some time until the network stabilized in the correct way. So this instability period is extremely interesting because it actually shows the kitchen of memory recollection, where you can test several hypotheses about how it's organized on a temporal way. So this is just teleportation from different perspectives. Here is the correlation with how the population should look like in room A. Here is in room B. You can see that the rat is running here, and the correlations are high only in room A in this case, but doesn't make sense in room B. So this is not teleportation trial. This is just decoding of the position. Here there is a teleportation trial. The rat is in room, let's call it red room. Now it's teleported into B, into blue room. And you could see, I'll run it in a slower way. So one frame is 125 milliseconds. This is the moment of teleportation, and in a next, let's say 100 milliseconds, you could see that the activity jumped here, but then occasionally it jumped back. So this phenomena, we call it flickering. It really reflects kind of competition between those attractor states as our brain is flipping between jar and faces. In this case, the hippocampus was flipping or flickering between a representation for both rooms. These are another examples. This plot shows you how quickly the network is able to respond. Majority of responses really came within first hundreds of milliseconds, and within first seconds, the network stabilized in the correct state. And I have to say, it always stabilized in the correct state. Sometimes, because we did it many times in a rat, sometimes it started to flicker spontaneously without any teleportation, any change in the external environment, as it was kind of expecting it or just wondering what's happening. I'll show it once again in a slower movie, and you can see that really every single theta cycle, which means 125 milliseconds, the network could change its state. Very importantly, this is kind of cartoon. These are all the spikes, all the action potentials that should happen in room A. These are all the spikes that should happen only in room B. Then you can bin the recording however you want. We use this theta oscillation, and clearly you can see that if you use this type of patterning, you get maximal separation between the states, because this will be state for room, let's say A. This will be kind of mix, but still state for room B, A, B, and so on. But if you use different bordering, you could get much bigger mass, much bigger or a much smaller resolution between those two states. And so we did it systematically, shifted the borders between temporal bins, and found this tuning curve that shows that the minimum number of mixtures between states occurs really around the border we chose, which was the phase of the oscillation related to the lowest activity in the network. And before I start to interpret it, this is another type of analysis. Then here we actually split each temporal bin, each 125 millisecond long window, into two halves, and found that with a higher probability in the first half, which is this one, the green halves, you can see mix between both populations of cells, between both states, more often than in the second half. That means that in the first portion of this theta cycle, which we believe is this kind of quantum of memory processing, the network can get confusing input, like seeing this drawing of either jar or faces, and starts to respond to it by mix of representations. But in the second half of the cycle, it simply decides whether it would go for face or for a jar. So you can see this pattern completion happening 9 times in a second in the network, so it can probably very quickly react to what's happening around. So to summarize, memory processing is compressed into kind of discrete temporal units. We believe it's reflecting the local theta oscillation, which is about 125 milliseconds. It really allows the memory to quickly retrieve proper memory states if something happens outside. And conflicting stimuli, for instance, those flipping pictures, or in our case, teleportation, which is a conflict between what the animal can see and what it remembers how it travels, can really initiate short-lasting, unstable states in the network. And if those are repeating often, it actually can create a new attractor states or merge between those two initially very discrete states of activity. Attractor theories are actually very interesting if you apply them to human cognitive diseases, like Edmund Rolls does for schizophrenia, for instance, because the depth of attractor, it should also it should depict the stability of the given state. If the schizophrenic patient is in kind of manic state, it really jumps across different states, being able to connect items or memories that we don't normally connect, and then ends up with hallucinations or paranoid states and so on. So in this way of thinking, the attractors actually are shallow. So the activity is not stably set in a given state. So what we do now is to kind of trying to continuously morph between those two different states, trying to understand how the network reacts. So this is 1 minute of continuous morphing between room B and room A. You can see how the network reacts to it. It very sensitively jumps back and forth. So I guess this is a great beginning for studying several models of human diseases, like a schizophrenic model in the rats or Alzheimer models, and try to understand how this kinetics is affected under these conditions. And eventually, if it turns out that it's connected with, for instance, impairment in oscillations, how eventually to treat it in terms of brain stimulation and so on. So thank you very much for your attention, and I'm happy to hear your comments, critics, and questions. Thank you.
Questions?
So thanks very much. That's really fascinating work, and I think the morphing experiment is going to be really interesting. Even the morphing experiment, though, as well as the alternation kind of experiment, is kind of within the hippocampal system. And I'm wondering, I kept thinking as you were talking about how to relate this to the kind of thing that Tim McNamara told us about at the beginning of the day. So these systems are really basically overriding head direction and grid cell information, since the animal is moving within the chamber, but it ought to, quote unquote, know that it hasn't actually moved from this training chamber to that training chamber, if I got the setup correctly. So in a situation that was less radical than pseudo-teleportation, but that wasn't morphing. In other words, if you do the kind of thing that Marco Nardini did, where you move the lights somewhat, if you have a situation where there's a competition between the various systems that make up the navigation system, is there any possibility, technically, I don't know if this is even possible, of diagnosing a situation that isn't outright conflict, but that instead would actually be a situation in which you might integrate or combine? Is that at all possible? Do you see what I'm saying? So I'd like to start to move beyond just the, am I in this chamber or did I weirdly teleport to this other chamber, which is still within the hippocampal system. It's place cells you're looking at.
Yeah.
What do place cells do? I mean, they're writing roughshod over the other information, presumably because they don't know what to make of the fact that there's no input from the other stuff. So they're just saying, okay, fine, I'm assigning a 0 weight.
Yeah, well, if I understand correctly, what we are looking at is a very hidden neural network in the brain, which gives such a great transparent picture about where the animal is, but we don't know much about the consequences or what else is happening with the representation before it reaches some effector and the animal can respond. And that's exactly kind of project we want to go for, meaning to record across different networks where you can still read at least which room the animal is in, networks that are interconnected. In this case, it means these data were from CA3, that signals for CA1, that signals out of the hippocampus to cortex. You know that in the prefrontal cortex, you can still see traces of room-specific activity. And we would like to do kind of triple recordings, or at least dual recordings across these networks, and to try to understand how this change, which I believe that's the core of memory recollection, spreads through the brain. So if the change begins in CA3, is it transmitted all the time into CA1? If it's reaching CA1, is it all the time transmitted to prefrontal cortex? Is this flickering something that reaches the cortex at all? Or is it just really
Yeah, I see what
cooking
you mean,
inside of the
right.
kitchen, and what comes out is something much more stable? So this needs to be done.
And now I'm beginning to understand your little casual comment about schizophrenia. Because what does it take for the brain as a whole to say, basically, I must be hallucinating? Yeah. Okay, thank you.
Thank you.
Your environments were rather uniform, and you had place cells locating areas. But then you said you found border cells. I mean, these are the non-uniform aspects of the rat environments. But my question concerns, have you looked at what happens if you introduce landmarks in the environment? If you have it slightly bigger, would that be coded in some specific way? I mean, border cells make sense from a point of view of the ecology of a rat, but I guess that landmarks would make sense as well. So is there any knowledge about how if there is any coding for landmarks?
Yeah, definitely. In different parts of the cortex that sends the signals into hippocampus, you can really see representation that is, or cells that are responsive to landmarks along the tray the animal is moving. I'm not sure whether this is published, but I saw Carol Barnes to report these data. But this is not hippocampus. If you look in hippocampus, which we believe stores certain types of memories, you can definitely see kind of incoherent distribution of those firing fields. In those rooms, those very simple rooms, even there you can see actual accumulation of fields along the walls, especially accumulation in the corners, which are something very important for this type of animals, who needs to hide actually, who like it. And if you would insert objects there, you would also see slight accumulation of fields around the objects, meaning that the system would code the given space reflecting its importance. That is not equal. The corners are more important than the center, and the same you can say for the object. So you can see the reflection of objects in hippocampus as well.
So I think I have a question that's related to both of these, and that's sort of taking it one step further. If you're in the hippocampus, I immediately begin thinking about associative learning. And so when does the rat, can you model, or can you do the experiment where the rat is introduced to cheese is in this corner when you do something or other, and then in the other room, you know, there's something else in another corner, or in the same corner, and so when can you look at the disruption of the learning experience, so that you've had one experience and then you've had a different kind of experience, but there must be some transition between these two experiences as you're flipping from one context to another, where you're not sure whether it was the cheese in the corner, or was it something else in the corner? And so that's just asking about sort of the next step of experiment, where you would be able to look at this in terms of learning, associative learning, instead of merely, which is an incredible feat, merely representation of the spaces. And then a related question, I was really glad you brought up the issue of clinical trials or clinical populations in the end, because one of the things I wondered about was Alzheimer's. Clearly, where you've got a case where their memory is being destroyed, and the question that I had, sort of one of the really naive ideas, is that the length of time during which you're oscillating between these states and not stabilized could be really, really drawn out if you were diseased. So both of those questions.
Yeah, we are really thinking about this very, very intensively, because typically Alzheimer, the patient can show you one day, let's say, good memory, and the second day it gets lost next to his house. So this means that the memory is still present in the brain, but just somehow inaccessible. So what does it mean? Is it something that just the network can't recollect it? Well, it must mean this, definitely. And I guess with this morphing, or just using the teleportation paradigm in Alzheimer rats, we can learn a lot, whether they are able to, for instance, recollect correct representation, which is something which is not behavioral response, but in a given situation, under given conditions, maybe they will be not able to respond in a behavioral domain, right? So one can actually expect all kinds of distractions. Maybe the hippocampus is working almost well, but the problem can be somewhere else, that the rat wouldn't go for the correct corner where it's used to find the cheese, for instance. So it would have correct representation for the room with the cheese, but not being able to respond. So this would point to different stages of spatial memory processing, for instance.
I have a very basic question, and that is the following. So you have shown a little network. The question is simply this. I mean, how did you identify the cells? And is that the network that is sort of supposed to do the tracking for all rooms? I mean, after all, a rat, it doesn't live in just one square, so there's many. So is there just one of them responsible, sort of, caching all sort of room states in one, or is there several? And what happens with what the rat is actually learning in terms of your configuration?
So if I understand correctly, you are asking how the process of setting the given state looks like when the rat is brought into a totally novel room, for instance.
Right, like we are learning to maneuver in very different locations.
Yeah.
So it's a very expanding knowledge, basically.
So actually we are doing this experiment right now. I mean, now we have a data and now we are analyzing it. So the rat was brought across 11 different rooms in the lab. In each, it could stay for 30 minutes and went into another one. So the rooms were very similar because it's a new lab. What the rat can see is basically all the same, and just those cues were in different constellations, so the rooms look a little bit different. I'm not able to say the difference, but the rat, at least their hippocampi, their representations were unique for each of those 10 rooms that were presented as a new rooms in one big sequence. So there is really large capacity for storing different rooms, different spaces. There are estimates, computation estimates, how many it can be. It's definitely, theoretically, thousands of them can be stored. And as you pointed also, the laboratory rats are, of course, very much impaired in their exploration of the real world. They are kept in very narrow conditions, and therefore, actually, I was also surprised that they could code 10 different or 11 different rooms without being trained in some kind of more complex environments and so on. So the capacity is high, and the hippocampus can simply manage to code for new information in kind of explosive way.
Sure, but just an indication of the magnitude. I mean, you were showing a dozen cells, right?
I can't hear you well, sorry.
You were showing us maybe a dozen or so of cells, right? And so you were pinpointing them, but I don't know, do you have any estimate how many you need? I mean, you say it's large, but you just looked at very specific parts of it. Do you see what I mean?
Well, if you record, you can record from, let's say, 100 cells. That's okay. All you can see out of million.
Okay.
And but still, those 100 cells, actually a fraction of them active in a given room, represent the whole representation the hippocampus devotes for the given space.
I begin to understand, yes.
Very quick last question from Tim. Oh, okay. Then, is there another quick question? Then, thank Carol again.
Thank you.
And is coffee downstairs?